Welcome to an introduction to bit manipulation. Let's start by understanding what bits are. Bits are the smallest unit of data in computing, represented as either 0 or 1. These binary digits form the foundation of all digital information. Bit manipulation is the act of algorithmically manipulating bits or other pieces of data shorter than a byte. These operations are extremely efficient because they're directly supported by processor hardware. In programming, we can perform operations directly on these bits using bitwise operators. The AND operator, represented as AND, sets each bit to 1 if both bits are 1. The OR operator, represented as OR, sets each bit to 1 if either bit is 1. The XOR operator, represented as CARED, sets each bit to 1 if only one bit is 1. The NOT operator, represented as SCAL, inverts all the bits. The left shift operator, represented as shifts bits left, filling with zeros on right. The right shift operator, represented as stray, shifts bits right, filling based on sign. Bit manipulation is used extensively in several key areas. These include cryptography for securing data, compression algorithms for reducing data size, and embedded systems programming where memory and processing efficiency are crucial. Bit manipulation operations are fundamental in low-level programming and offer significant performance advantages due to their direct hardware support. Let's explore common bit manipulation techniques. First, checking if a bit is set at a specific position. We use the AND operator with a mask. Let's work through an example. We want to check if bit 3 is set in the number 42. First, we look at 42 in binary, which is 00101010. To check bit 3, we create a mask by left shifting 1 by 3 positions. This gives us 000100 with only bit 3 set to 1. Now we perform the AND operation. If bit 3 is set in our number, the result will be non-zero. Our second technique is setting a specific bit. To set a bit, we use the OR operator with a mask created by shifting. Let's set bit 2 in the number 37. First, we look at 37 in binary, which is 00100101. We create a mask by left shifting 1 by 2 positions. This gives us 00000100 with only bit 2 set to 1. Now we perform the OR operation. This ensures that bit 2 will be set to 1 in our result, regardless of its original value. Our third technique is clearing a bit. To clear a specific bit, we use the AND operator with the complement of a mask. Let's clear bit 1 in the number 43. First, we look at 43 in binary, which is 001011. We create a mask by left shifting 1 by 1 position. This gives us 00000010. Then we take the complement of this mask, flipping all the bits. This gives us 111101 with only bit 1 set to 0. Now we perform the AND operation with the original number and the complemented mask. This ensures that bit 1 will be cleared to 0, while all other bits remain unchanged. Our fourth technique is toggling a bit. To toggle a bit, meaning to flip its value, we use the XOR operator with a mask. Let's toggle bit 2 in the number 41. First, we look at 41 in binary, which is 00100101. We create a mask by left shifting 1 by 2 positions. This gives us 00000100 with only bit 2 set to 1. Now we perform the XOR operation. The XOR operation flips the bit where the mask has a 1 and leaves other bits unchanged. As we can see, bit 2 has been flipped from 0 to 1, changing 41 to 45. Another useful technique is the XOR swap algorithm, which allows us to swap two values without using a temporary variable. Let's see how this works by swapping two values, A equals 25 and B equals 42. Here are their binary representations. In step 1, we set A equal to a XOR B. This gives us A equal 51, while B remains 42. In step 2, we set B equal to B XOR A. Since A now equals 51, this operation gives us B equals 25, which was our original value of A. Finally, in step 3, we set A equal to a XOR B. Since B now equals 25 and A equals 51, this gives us A equals 42, which was our original value of B. And just like that, we've swapped the values of A and B without using a temporary variable. This technique is particularly useful in memory-constrained environments. Bit shifting operations can also be used for efficient multiplication and division by powers of 2. For multiplication, left shifting a number by n bits is equivalent to multiplying it by 2 raised to the power of n. For example, to multiply 7 by 4, we can shift left by 2 bits, since 4 equals 2 squared. This moves each bit 2 positions to the left. Similarly, for division, right shifting a number by n bits is equivalent to dividing it by 2 raised to the power of n. For example, to divide 24 by 8, we can shift right by 3 bits, since 8 equals 2 cubed. This moves each bit 3 positions to the right. These bit-shifting techniques are particularly valuable in competitive programming and resource-constrained systems, as they are much faster than standard multiplication and division operations.